Okay, welcome to the lab. Like I mentioned, we're just going to kind of finish the last couple of slides on double displacement reactions since our lab today is study assignment E, I think, which has to do obviously with net ionic equations and stuff that we've been talking about here. Okay, so we've been talking about double displacement reactions, which again, as I mentioned, is sort of a big classification of reactions. And one type of double displacement reaction is what we've been talking about mainly here, which are precipitation reactions. And again, precipitation reactions are reactions that basically yield some type of solid product, which is obviously known as a precipitate. The way you can determine that solid product is, as we were talking about there during lecture as well, using the solubility rules to determine if something is going to be soluble, which means it'll be aqueous and no solid form, or something that will be insoluble, which means you'll get a solid symbol and some type of solid or precipitate would be formed. Any questions on those type of reactions? Again, we could write a molecular equation, which is everybody together in their whole formulas. Balanced with their sort of states. We could write a total ionic equation, which breaks apart everything that's a strong electrolyte. The only things that you would leave together and not break apart in that total ionic equation are the things that we talked about, which are essentially solids, liquids, gases, and anything that you can see is a weak electrolyte you would keep together. Usually when you get to that total ionic equation, you'll have some ions on both sides of the arrow, which are known as spectator ions, and they should look exactly the same on both sides, and they really should cancel out completely. So again, you know probably something's wrong with your balancing or something like that if you get to that point and your spectator ions are not really canceling out completely, like you got two on one side and one on the other. Something's probably not right, either the way you balanced it or the way you wrote the formula. Once you find those spectator ions, you basically get rid of them, and that leaves you the net ionic equation, which again is essentially the actual reaction that's taking place. So it's really the main reaction that's happening when you, for example, mix those two solutions together. So we're going to talk then about another type of really double displacement reaction, which again, this type of reaction we're going to talk about here does fall underneath that umbrella, but it also is sometimes referred to as acid-base neutralization reactions, but ultimately they are double displacement reactions that are occurring. So we're going to talk a little bit about that here. So let's just talk a little about acids and bases just in general. In general, acids ionize in water basically to form H plus or H3O plus. And when you talk about acid and bases, which you will if you plan on taking 200B a lot, H plus, which is the hydrogen ion, and H3O plus, as we might have talked about a little bit before, is the hydronium ion. And they're pretty much interchangeable in sort of acid-base chemistry. They basically represent the acidic part of the solution. Bases, on the other hand, are things that are able to produce hydroxide or OH minus in solution. And that's one way you could usually determine whether you're sort of dealing with an acidic solution or a basic solution is when you look at your correctly sort of balanced equation. If on the product side you got some hydroxide there, it's probably basic type solution. If on the product side you have H plus or H3O plus on the product side, it's probably going to be more of an acidic type solution. But there is a general reaction that occurs when we take like a strong acid and a strong base together, and we typically always form a salt and water. And those are the two things that are formed when we react an acid with a base. A salt is really just a fancy word. I'm not sure how fancy it is, but really a fancy word for an ionic compound. So it really is just something that is a positive ion, negative ion together, cation, anion, like sodium chloride, for example. It's a salt. Water is, hopefully, you know, H2O, or hopefully that is H2O. And that is typically what you will always sort of produce when you take really a strong acid and a strong base together. And the basis of that is really the acid what makes something an acid is the H plus that it can kind of give away. And what makes something the base is sort of that OH minus. And that's really where our water comes from. The H plus from the acid, OH minus from the base, in a strong acid, strong base combination, you know, is really where we get that H2O sort of being formed. And that's why when we do take an acid and base together, as we will see, is sometimes also referred to as a neutralization reaction, because essentially water is being formed. Here's a table, and I think you have a sort of similar table somewhere in your book there. These are some strong acids, some weaker acids, and stuff like that. These are our groups of sort of strong acids here. We have perchloric acid, nitric acid, sulfuric acid, hydrochloric acid, a couple others you could add to that list. HBr is a strong acid. Hydrobromic acid, hydriodic acid is also a relatively strong acid. And then down here are some weak acids. You have your acetic acid, which is our vinegar. HF, HNO2 as well is a weak acid. HCN is also a weak acid. So these are some weak acids. So strong acids are really strong electrolytes. So if you have any of these sort of strong acids, they will 100% break apart into ions. Weak acids and stuff like that are considered weak electrolytes. So if you come across sort of a reaction that involves HF, for example, and you got to the total ionic equation part of it, you would actually keep the HF together, because again, it's a weak electrolyte. So you wouldn't break it apart into its ions, and you would actually keep it together. So these are very common sort of weak electrolytes to sort of pop out in, you know, sort of these total ionic equations, net ionic equations, and stuff like that. So if you could recognize it as sort of a weak acid, when you would get to that part, you would keep it together. If you could recognize it as a strong acid, it should be a strong electrolyte, and you would break it apart. Here are some bases, and as we talked about, a lot of strong bases will actually have hydroxide in it. And typically the hydroxide will be hooked up with somebody from group 1 or group 2 of the periodic table. So again, if you kind of go down the periodic table there, kind of sodium hydroxide, potassium hydroxide, hang a right, calcium hydroxide, strontium hydroxide, barium hydroxide, so kind of that move there. Typically are your strong bases. So same idea, if you had any type of double displacement reaction where you would get to a total ionic equation and you had any of these strong guys, you would 100% break them apart. NH3 is a weak base. Most of the time you see it as NH3, which is ammonia. And if you had something like that, or NH4OH, which is also sort of a version of ammonia and water, you would kind of keep those guys together. Again, they would be more of a weak electrolyte and wouldn't break apart 100%. So when we do put a strong acid and a strong base together, it is sometimes again referred to as a neutralization reaction. And that's because essentially the main reaction that's happening here, if we look at something like hydrochloric acid, which is a strong acid, and sodium hydroxide, which is a strong base. Just first off, if you look at this, even though it's an acid-base reaction, this is really a positive negative guy. This is really a positive negative guy. And what's ultimately happening here is our two positive guys are switching partners. You know, this is technically H plus and Cl minus, as it's a strong acid. This is Na plus and OH minus because it's a strong base, so it would break apart. On the other side here, we have NaCl, which will break apart as well. Grab an eraser here. There we go. Na plus and Cl minus. Now, water here is a pure liquid. It will stay together. So again, we do not break apart the water here as it's a liquid. And this would be our total ionic equation. And what I was trying to sort of write here before I tangented there, what we have is essentially a double displacement reaction. So the H is going to hook up with the OH. So again, the H plus from our acid, the OH minus from our base, those two come together and that is how we get the water that's there. The salt comes together from the opposite two things, the sodium coming together and our chloride. So again, our salt and water in this particular case. Now, if we do our total ionic equation like we got going on here, total ionic, and we look at spectator ions here, we have sodium on both sides. We also have chloride on both sides. And if we get rid of our spectator ions, we are left with H plus from the acid coming together with OH minus from the base to form H2O, which is our liquid, and really why we do call this a neutralization reaction, because really the main thing that you're forming in this case is water. Now, if you did this reaction and you looked at it, it wouldn't be very exciting because you pretty much wouldn't see anything, because you can't see, I guess you can see water, but you can't really see water being formed, I suppose. So unlike a precipitation reaction where you could actually see the solid happening, in this type of reaction, you wouldn't be able to see it, but you're actually forming water here. And that is the main reaction that is taking place here. And that is the net ionic equation for pretty much any combination you do that is a strong acid and a strong base. You could put together any combination, and if you get to the net ionic equation, it will always be the formation of water. So if I swap this around and did nitric acid, which is a strong acid, with potassium hydroxide, I would form KNO3 and H2O. Again, H from the acid, OH from the base coming together to make my water, K and the NO3 minus coming together. Again, if I broke that apart, I would have H plus NO3 minus plus K plus and OH minus, making K plus and NO3 minus and H2O. Spectator ion being nitrate on both sides, potassium on both sides. And again, you can see I am left with the exact same reaction. I am left with H plus OH minus, making water. And putting in our states here. So strong acid, strong base, 100% of the time, always makes a salt and water. Always 100% of the time, any combination of those two things, a strong acid with a strong base, will always end up in a net ionic equation of H plus OH minus makes H2O. That's always what you get in that reaction. Question on that there. Sort of what I scribbled there, I think. And here's, again, sort of that reaction. Now, just to sort of show you maybe what happens if we don't use a strong acid and strong base, but perhaps if we had a weak acid. So let's just say we did have HF plus our sodium hydroxide. Now, in this particular case, it is going to still be a double displacement reaction, positive, negative, positive, negative. Again, we're going to get the water from the H from the acid, the OH from the base. That's going to make our water. And our sodium, which is +1, and our fluoride, which is -1, will come together to make sodium fluoride. So this would be our molecular equation here, H2O plus NaF. NaF would be our salt, and H2O obviously would be our water in this particular case. Now, when we would go to our total ionic equation in this particular case, the HF we would recognize hopefully as a weak acid, which means we would actually keep it together. And we would write our total ionic equation would look something like this. The HF would stay together. The sodium hydroxide would break apart. And go on the other side here of the picture. On the other side, we will have our water, which will stay together. And our sodium fluoride would also break apart. So this is what our our total ionic equation would look like. Again, because this is a weak electrolyte, we keep it together when we get to this part. Any questions on that there? Now, the importance of keeping that together is when we look at this equation and we look at spectator ions, there is actually only one spectator ion in this one. It is actually just the sodium ion that is the spectator ion. There is no other ion on both sides that looks exactly the same. We don't have the fluoride or anything like that because we did not break it apart. So the only spectator ion in this case would just be the sodium, and we would be left with our net ionic equation, which will look like this. Again, our HF still together, plus our hydroxide. And because really it's a weak electrolyte, you actually would have the two arrows. Not super important for our class, but that's probably what you would have going on there. We would have our water plus our fluoride here. And this would be our net ionic equation in this particular case. So hopefully you can see with this example that if you can recognize something as a weak electrolyte, in probably our case, it will probably be some type of weak acid you might come across or something like that, maybe a weak base. What you want to do when you do get to that total ionic equation, like I just did here, is still keep it together. And usually what you'll end up with is really only kind of one spectator ion to kind of break apart. Question on sort of this with a weak electrolyte. So ultimately, this is still a double displacement reaction happening. It is probably most often classified more so these guys as acid-base reactions because it involves obviously an acid and base. But ultimately, again, sort of that big umbrella, we have precipitation reactions like we talked about. We also have here acid-base reactions, which typically will form water as a double displacement sort of reaction that takes place. And there's also some double displacement reactions that will end up actually producing some gases as a result of the reaction that will take place. So let's talk about some of those type of reactions. And these are, again, double displacement reactions where our product or a product of it is actually going to be a gas. And sometimes this gas is formed sort of directly by the direct double displacement. So for example, this is an example of a direct formation of a gas. So this would be our positive negative guy. This again is an acid, positive negative guy. This is potassium sulfide plus sulfuric acid. Again, a double displacement reaction, potassium and the sulfate coming together over here. The H and the S coming together to make hydrogen sulfide gas, deadly toxic yellow gas that you play with in 200B. Maybe not so much anymore, I suppose. But it's very smelly. Sulfur stuff does not smell very good usually. But this is basically a gas that's generated directly as a result of this. Again, here, if you were going to get to your sort of net ionic equation, what you would do, right, is you would have your K plus that would break apart, your sulfide, your 2H pluses, and your SO4 2 minus. I won't write the states in because I'm going to run out of room. We'll have our 2K pluses, our SO4 2 minuses. Now we have a gas here, and that gas would stay together as H2S. So again, we would not break apart that gas. So solid, liquid, gas would stay together. In this case, our spectator ions would be our couple of potassiums. It would also be our sulfate. And ultimately what's happening here is our two hydrogens are coming together with our sulfide to form our H2S gas. And again, this would be our net ionic equation that's happening here. So again, solid, liquid, or gas, when you get to that total ionic, you do want to keep it together. Question on that there? Now, another very common route that a gas can be generated in a double displacement reaction is our bottom one here. It looks very similar, but this is potassium sulfite plus sulfuric acid. Again, double displacement here, our potassium and our sulfate coming together, our H2 and our sulfite coming together here to make sulfurous acid. So that's H2SO3, that's sulfite, right? It's an acid, AQ, which makes it sulfurous acid. Sulfurous acid, this first reaction is a double displacement reaction. But the actual sulfurous acid actually then goes through a second reaction. And this, as we'll see later on in this chapter, this is what is known as a decomposition reaction. So a decomposition reaction occurs with one of the products. It basically decomposes into water and SO2 gas, sulfur dioxide gas, and the bubbles that you see here, basically. So that is a sort of indirect formation of a gas, where typically one of the products will then continue to react and go through a decomposition reaction and produce a gas in that route. So these are two sort of common ways that a gas can be generated, one sort of a direct generation of the gas, the other one sort of an indirect generation, sort of a two-step process, a double displacement reaction, followed by a decomposition reaction of one of the products. Any questions on that there? And this is also a very common one here. This is sodium bicarbonate, positive, negative, positive, negative. This is sort of the end result of what you get. But if you think about these two guys, that's Na plus and hydrogen carbonate, that's H plus and Cl minus. These two guys will come together in this double displacement, and these two guys will come together. And really what you get on this side is your sodium chloride, as you can see, and the H, which is H plus, and our, I'm sorry, I forgot the Na there. There's our Na. I'm sorry, HCO3. We get our H2CO3 coming together in this particular case. And this guy right here is carbonic acid, much like sulfurous acid. If you remember, our sulfurous acid broke apart, and that's exactly what happens here. The carbonic acid very, very quickly will break apart into CO2 and water. CO2 is the bubbles that you see, plop, plop, fizz, fizz, Alka-Seltzer, all that good stuff. That is what you're seeing is that CO2 gas, and that's why it says CO2 and water here. This again is a double displacement followed by a decomposition reaction occurring of the carbonic acid to make CO2 and water. So again, this would be an indirect gas generation. And if we were to write our net ionic equation here, we would keep the CO2 and the water together in this case. And probably the only spectator ion you would have going on, actually the sodium, the chloride, I think would go apart as well. So those would be the two guys I think that you would end up with. So here's a nice little table that sort of describes some of your different combinations and what you typically will get. If you take a metal that has just sulfur in it, and are a metal with HS and you react it with an acid, this is usually the gas that you will generate, which is hydrogen sulfide gas. No decomposition, it's a direct sort of formation of that. If you take a metal like sodium carbonate like we just saw, or sodium bicarbonate like we just saw, and you react it with an acid, you will generate carbonic acid. That will go through a decomposition reaction and it will yield carbon dioxide gas. If you take a metal like sodium, potassium sulfite, or potassium hydrogen sulfite and react it with an acid, you'll get that other one that we saw, which is sulfurous acid, which will go through a decomposition and make SO2. So the combination there is CO2 and SO2. And if you have ammonium and a negative guy, and you react it with a base, you will make ammonium hydroxide. Ammonium hydroxide is basically the water version of ammonia. And in water, it will decompose into basically NH3 and make ammonia gas. So these is a nice table to sort of indicate, you know, those sort of direct routes or indirect routes of gas formations. So double displacement reactions, which is again the big category, you can go kind of more specific in those type of reactions where we have a precipitation reaction where we form a solid. You can get an acid-base reaction where we're basically forming water. You can also get a double displacement reaction as we see here that will generate some type of gas. Any questions on any of that stuff there? All right, so that's where I want to kind of get to. That should help you, I think, in what's going on for today. So for today, up on tap is, I believe, study assignment E. So that is study assignment E. And surprisingly enough, that's all about net ionic equations. Yeah. So you are going to have a bunch of different sort of reactions. Some may be double displacement reactions. Some may be acid-base reactions. Some may generate a gas. Some may have a weak acid involved, and those type of guys. So you're going to be asked to write sort of your net ionic equations for those, I think, mostly. Maybe some total ionic equations and stuff like that. I will say, just so you know, that if, you know, for example, if you wanted to just get to the net ionic equation, you can sort of work backwards, especially if you know sort of what is being formed in terms of a product. So for example, we had, say, something like silver chloride we saw in one of those guys. Especially in a precipitation reaction, if you know that one of the guys are going to make a solid, as you hopefully have seen in all those ones where we go from molecular equation to total ionic equation to net ionic equation, our solid basically stays together. So you could almost work yourself backwards and start with the solid and go, this solid is basically made up of a silver ion and a chloride ion, and you will have your net ionic equation pretty quickly. For example, we had lead to iodide, I think, as well. Again, if you just kind of break this apart correctly, that would be a lead ion and 2 iodide ions. And that would be your net ionic equation. So, you know, especially if you have a sort of a solid, you can just sort of break the thing apart and work backwards, and it will usually bring you to the correct net ionic equation. Even if you had something like water, for example, you can know that that's going to be H plus and OH minus. That's essentially what we should think of water as, is H plus and OH minus, and you work your way backward. The only thing you have to watch out for, right, is if you got some type of weak electrolyte somewhere, it needs to be in there as well. But if everything's sort of a strong electrolyte and you're only left with the solid or something like that, you know, you could kind of work your way backwards from the solid product, and you could kind of get to the net ionic equation really quickly. I will say that I think there may be only one in this study assignment, which is a single replacement reaction, which I think we've talked about in a previous sort of experiment. But it's basically a hydrogen displacement. So for example, if you had a metal plus some hydrochloric acid, what's going to happen in this case is, again, as I think we talked about before, the metal will come in and kick out the positive guy. And this is a single replacement reaction. We have a metal plus something that's ionic. And when it does, the metal will gain a charge and hook up with our nonmetal. And when hydrogen always comes out, it always comes out as a gas, right? And by itself in a sort of diatomic form. And if you did a little bit of balancing, maybe a 2 there in that particular case. So if you had a net ionic equation for this guy, you would follow the same sort of rules. Zinc would not break apart because it's a solid. HCl, which is a strong acid, would break apart into a couple of hydrogens plus a couple of chlorides. Zinc would also break apart into zinc with a +2 and a couple of chlorides. And H2, which is a gas, would stay together. This would be your total ionic equation here. And you would look for spectator ions on both sides, and hopefully you will see it's actually only the chloride in this case. The H pluses do not cancel out because H2 is not an ion on the right, and they don't look exactly the same. And what that would leave you is the net ionic equation, which will look something like this. And as you can see here again, things that are solid didn't get broken apart, things that are gases stayed together. We just kept everything together, and this would be our net ionic equation. And this is basically a redox reaction, which is the next big sort of topic in terms of reactions and stuff like that, which of course we will save for Thursday. But I think you might have one type of reaction similar to this. The other kind of weird thing that you'll see, I think, in the study assignment and throughout a lot of sort of the experiments is, actually we'll do it here. Water, which is H2O, it's oftentimes written HOH. So you'll oftentimes see water in these things written as HOH in your lab manual. And I think the purpose of them writing it as HOH is so you could kind of think of it as H plus and OH minus. So that sort of idea. And also in a reaction like this, if it reacted with water, it would be like it reacting with just that H, and you would still have the OH. So if you see HOH, I like to write H2O personally, but you know, it's okay, I guess. In the lab manual, they use HOH a lot to represent water. So study assignment E is pretty much all that. It's writing ionic equations, total net ionic equations. You have some where you have just the starting stuff, just the reactants, and you got to predict the products. So make sure, again, that you get the right formulas down first, and then you balance it. You also have some that you need to read really carefully because what they give you in words is the products, not the reactants. So make sure you read it really carefully. It's a very common mistake people make is they read it, and what they read is they just assume it's the reactants, but you're actually given the products, and you got to think about what it came from. So make sure you read, especially those ones that are all words, make sure that you do read it really carefully. And again, make sure you start with the correct formulas. Make sure you get everything balanced. Yes, so everything should be balanced all the way through your molecular equation, your total ionic equation, and your net ion equation. They all should be definitely balanced, I think, in that. Any questions on that there? So I'm going to officially make it due the latest on Thursday. You could turn it in obviously before then if you want to, but the latest will be Thursday. And again, a reminder that the next exam is a week from today. Your quizzes should be graded, so you should be able to see how you did on those. And other than that, if you have questions on this, I'll be more than happy to answer. If you have questions on anything else, we do have an exam coming up. I'll be happy to answer those questions as well. Other than that, then go work on something. I think the Dodgers almost came back. I'm not sure. The ninth inning there. If you have questions, feel free to hang out. If you haven't put here, please do so.